Hi everyone, today we'll talk about my project on effective resistance random walking algorithms. First, we must understand what our large electrical network is. Mathematically, one models an electrical network using a weighted graph, consisting of vertices and edges, together with a resistance or weight function to determine each edge. One encounters electrical networks all the time. They could be literal networks or may model complex networks of social relations. Weighted graphs. In the context of any weighted graphs, the Laplacian operator can be defined to be the following, where f of x represents the value of the function f at vertex x, w sub xy denotes the weight of an edge that connects vertices x and y, and the summation is taken over all neighboring vertices y of all x. In this weighted graph setting, Lf of x calculates the difference between the value of the function f at vertex x and the weighted average of f over all of its neighboring vertices. Now, let S of n represent the position of the random walk at time n. Formally, a simple random walk in one dimension can be defined as follows. The random walk starts at a specific initial position of S sub 0. At each time step, the walker takes a step to the left with probability p, or a step to the right with probability 1 minus p. The size of each step is usually fixed to 1, so the walker can only move 1 unit at one time. Position S of n at time n is the sum of the individual steps taken by the walker up to that point. So S sub n is equal to S sub 0 plus x1 plus x2, etc. to xn, where x sub I represents the size of the ith step taken by the walker at time I. Random walk on a graph is a process that begins at some vertex v. The vertex the walk moves to is chosen uniformly at random among the neighbors of the current vertex. Similarly, for an electrical network, it only moves to a neighbor with probability proportional to the conductance for the corresponding edge. The starting vertex v is very important. An event can have very different probability depending on the starting vertex of the random walk. Effective resistance. The Laplacian matrices of graphs arise when one models all electrical flow in networks of resistors. The edges correspond to resistors, with the weight of an edge being the reciprocal of its resistance. If P denotes the vector of potentials and I the vectors of currents entering and leaving vertices, then these satisfy the relation L is equal to I. The effective resistance between vertices U and V is the difference in potential one must impose between U and V to flow 1 unit of current from U to V. That's clearly defined in the definition below. Lastly, we will show our linear algebra algorithm. For the last section, finding effective resistance boils down to solving a linear equation involving Laplacian L. The process of doing so is as follows. First, construct a graph of the resistor network. Then evaluate individual resistance, which are the edges connecting the nodes. Indicate a starting node and an ending node. Mark them as node 1 and node n, where n is the number of nodes in the network. Then, construct a Laplacian matrix for this set of resistor network. For each entry L sub ij, for I equals j and L ij less than n, the value is the sum of all resistance at node I. And for each entry Lij for I not equal to j, Lj is equal to the resistance of the edge connecting to the nodes I and j. It is obvious that our I matrix is from 1 to -1, where there are n rows, depending on the number of nodes of the electrical network. Now we set up the linear equation of matrices to calculate the effective resistance, P1 to Pn, where we aim to find this matrix using an algorithm. Finally, taking the absolute value of Pn minus P1 is the effective resistance we are looking for. The framework we developed to find effective resistance has further implications beyond a mathematical algorithm. Here's an image of potential ways where you can employ this algorithm into more general settings.